This video is for the image formation lab for Physics 1102 and 1220. First, we're going to look at part A, which is examining brightness and magnification. Now, when you first open up the simulation, the default is that the convex lens is selected. You can also select the concave mirror, but for part A, we want to use the convex lens. And as per our diagram in the lab manual, this screen with the arrows on it is our object. Our convex lens is the football-shaped thingy in the middle. And then we have our white screen that will capture our focused image. And the definition of the object distance, DO, is from the object to the lens, or can also be from the object to the mirror if you are using the mirror. And the image distance is defined as the distance from the image to the lens, or again, can also be the distance from the image to the mirror if the mirror is being used. So, you're going to start off by placing the image screen at 70 centimeters. And you can move the image screen by clicking and dragging it with your mouse. So you'll notice that along the bottom we have a ruler in centimeters, and we have markings every 10 centimeters, as well as 1 centimeter divisions on that ruler. And then you're going to bring the lens very close to the object, roughly within 2 centimeters, and you'll examine the image screen and watch for where the image becomes focused. So by clicking on the lens and slowly moving it along the ruler, keeping an eye on our image screen, and now we're starting to see the arrows take shape, and eventually you'll find a position for the lens where the arrows form their most clear image. So you can look at the magnified image as well, and you're looking for very sharp edges, sharp corners, and no blurriness. You may find that there is some physical uncertainty in the lens position where the most focused image occurs. So to test this, you can try moving the lens a little bit backwards or a little bit forwards along the scale to see if there is some uncertainty in finding exactly where the image appears the most focused. In addition to that physical uncertainty, you will be recording the object position, the lens position, and the image position along the ruler as your data so that you can calculate your object and image distances. And because we have a ruler with divisions on it, you will need to include a reading uncertainty in all of those positions, as well as potentially a physical uncertainty. Now, you're going to examine the principle of reversibility. That means that with the image screen at the same location, you're going to continue to move the lens along the ruler, and you should find a second position where you have a focused image. And the principle of reversibility predicts that the object and image distance values are reversed, and there's also a relationship between the magnifications of those two images. So you will be collecting data for the image screen at various locations and examining that relationship between object and image distance and magnification. Now, for the purposes of Part A, in the calculations. I would be fine if you leave out uncertainty in the magnification calculations. This is so that you can make qualitative comparisons to verify the magnification, meaning you are using word descriptions as opposed to numbers with uncertainties. This is only for part A, and this is just to cut down on the amount of calculations involved in this experiment. When you are ready to collect data for part B to examine the thin lens equation, you may reuse some of the data that you collected in part A, meaning you can reuse the measurements of object, lens, and image position where you had the image screen at 70, 75, 80, and 85 centimeters. However, you will need roughly 8 to 10 data points in order to graphically verify your equation, and you should explore the full range of the ruler. For example, you will want to make a measurement where you place the image screen at the very end and move the lens along the track to find your focused image. And you can also play around with moving the lens and the image screen closer to the object and see what the minimum distance you can find for object and image distances for a clear focused image. There is a minimum distance where you'll be able to find a focused image, so you won't be able to go as close as possible. So something like this, you will not be able to find a clear focused image. When you're ready to collect your data for part C, you'll want to go to the upper left corner and select the concave mirror. And notice now that the mirror is on the far end of the track and the image screen is basically the two positions have reversed compared to the lens and the image screen. So the object distance is still defined as the distance from the object to the mirror. So from here all the way over to here. And then the image distance is still defined as the distance from the focused image to the mirror. So keep that in mind when you are doing your calculations. And you want to collect another roughly 8 to 10 data points in order to plot a graph to verify the mirror equation. So you can begin with the mirror at the end of the track, and then you'll need to move the image screen around until you can locate a clear focused image. And you'll want to consider the same uncertainties as you'd done previously with the lens. So consider the reading uncertainty using the ruler on the track, and then consider any physical uncertainty for locating exactly where your image is the most clearly focused. And again, you'll want to use the full range of the track, or as much of the track as you can. So moving inwards, and again, finding your clear image, moving inwards, finding a clear image, until you have enough data points to plot a graph and to verify the mirror equation. So now I'd like to talk about the graphing predictions and how we're going to verify equation number 1 graphically. So as per the lab manual, this equation number 1 here, this is not a linear equation. So if you were to plot DI versus DO, you wouldn't get a straight line, you'd get something else. But we can use the linearization technique that we learned in physics 1101 or 1120, and we can rearrange this equation and compare it with the equation of a line. So we have our equation 1b, which has moved 1 over dO to the other side of the equation. So we have 1 over di is equal to negative 1 over dO plus 1 over f. And if we then line this up with the equation of a line, so if we write y is equal to mx plus v, then we can see that we have our y variable should be 1 over di, and our x variable should be 1 over dO if we want to get a straight line graph. And I'm just going to write in a 1 here. So this is technically -1 times 1 over dO. And now we can see that according to our graphing theory, our first prediction is that if we graph 1 over di on our y-axis and 1 over dO on our x-axis, then we'll get a straight line graph. Then our predicted slope value is equal to just -1. And then finally, our predicted y-intercept value is equal to 1 over f, or 1 over the focal length. So when you want to verify your thin lens or your mirror equation, what you'll need to do is plot this graph and then check to see whether or not the graph meets all of the predictions. In this case, we don't have a predicted value for the focal length, so we won't have a predicted value for the y-intercept. That means you'll have to evaluate your graph solely based on the first two predictions. So prediction number 1, was your graph linear within uncertainty? So remember that if we have 1 over di versus 1 over dO, you have your data points with their uncertainties, and the uncertainty bars form a little box. Excuse my rough drawing. And the graph is considered linear with an uncertainty if and only if the line of best fit passes through all of these uncertainty boxes. So it doesn't necessarily have to be touching all of the points, it just has to pass through the uncertainty box somewhere. And then our second prediction is that the slope should be equal to -1. So using line graph, you're going to plot your data, and line graph will automatically calculate the value of the slope as well as its uncertainty. And you'll need to compare to see whether or not your experimental slope agrees with an uncertainty to our predicted value, which in this case is -1. And then finally, although we aren't able to make a comparison with the predicted value for the focal length, you're still able to calculate an experimental focal length because we have our prediction for the y-intercept. So the y-intercept should be equal to 1 over the focal length. And again, from your line graph, you will get a value for b, the y-intercept, as well as its uncertainty. And using this prediction, you'll be able to solve for the focal length. And from your experimental value of b, you'll be able to calculate the focal length and its uncertainty based on your graph. So that is how you will obtain the focal length of your lens and of your mirror. So you'll have two separate graphs. You'll have 1 over di versus 1 over dO for the lens and one for the mirror. So you'll have to evaluate each graph individually to see whether or not the lens and mirror equations have been verified. And I just want to comment a little bit on the uncertainty propagation. So I'm not going to go through the entire derivation like I did for the refraction lab, but it may be helpful when you are trying to find the uncertainties for plotting your graph. You may want to write an equation where you have y is equal to 1 over di, because that's going to be your y-axis. And remember that 1 over di is the same thing as di to the power of -1. And di is the image distance, so you will have to calculate that from the relative position of the image and the lens or the mirror. Because your measurements will have uncertainty, di will also have uncertainty. And then to figure out the uncertainties to plot on your graph, you'll use the calculus equation. We only have one variable here, so we have the partial derivative of y with respect to di times the uncertainty of di. And normally this would be square rooted and squared, but because there's only one variable, we know that it's going to simplify just down to this. So you'll have your delta di value, that'll go along with your di, and you'll need to calculate this partial derivative in order to determine your uncertainty for your y-axis. And you can follow a similar process to get the uncertainty for your x-axis. So the x-axis is going to be equal to 1 over dO, which is the same thing as dO to the power of -1. And using the calculus formula, we have uncertainty of x. So the uncertainties you're plotting on your x-axis are going to be partial derivative of x with respect to dO times the uncertainty of dO. And then absolute value because the uncertainties are plus or minus. And then finally, when you are trying to find the uncertainty of your measured focal length, recall that our predicted y-intercept says b is equal to 1 over f, which means that our f is going to be equal to 1 over b, which is also b to the -1. So again, you're going to follow a similar process to figure out the uncertainty of the experimental focal length for both the lens and the mirror.